But now we are going to go for a special case of the capacitor. We are going to consider a capacitor called as leaky capacitor, which is going to have a high resistance RP in shunt. So this diagram is wrong. Here you will be having a capacitance with the shunt resistance RP. So practical leaky capacitor will not have a series resistance. It will have a shunt resistance RP in parallel to C. That capacitor is called as a leaky capacitor. And we are going to derive what is the Q factor of a leaky capacitor. Okay. So now you see the circuit has become parallel RC. And you know, for parallel RC, I have given the formula Q is equal to R by X. And you know X is 1 by omega C. So the R by 1 by omega C. So if you simplify, you should get the answer as Q is equal to omega C R. We'll see whether we are getting this answer here. We should get the answer as Q is equal to omega CR. We'll check here. So maximum energy stored per cycle is same, half CF, half EVM square, where VM is the peak voltage applied to the capacitor, and average power dissipated per cycle in RP is VM by root 2 the whole square into 1 by RP. It is 1 by RP because it is in shunt now. Okay, so it is in shunt, so I'm going to take 1 by RP. So VM square by 2 into RP. Okay, and energy dissipated per cycle, convert the power into energy, so multiply this term by time. So VM square by 2 RP into T. See, previous case we used IM square into RP. Here I'm using VM square by RP. So that is why I'm getting 1 by RP term here. Okay, so I'm using the term VM square by RP because I know what is the input voltage and the maximum value. So directly I can use that. And by converting this energy power into energy, I'm going to multiply by time, and I'm replacing time by 1 by frequency. So now substitute, we have the expression for energy dissipated per cycle. We have the expression for maximum energy stored in the capacitor. So substitute everything, and now divide in the Q formula. Q is equal to 2 pi into maximum energy stored in the capacitor. So it is half CVM square divided by energy dissipated per cycle. So it is VM square by 2 RP into F. So this 1 by 2 will get cancelled. 2 pi F will become omega. VM square will get cancelled. This RP will go to the numerator. So it is omega C into RP. So we have theoretically written the expression using the formula. We got omega CR, and resistance value here we take it as RP. So we got the answer as omega C into RP. So this is the quality factor of a leaky capacitor. So normal practical capacitor will have C in series with R, but for a leaky capacitor, where the energy is not efficiently stored, we represent this inefficient nature of energy storing by the capacitor by a parallel resistance RP, which will be in shunt with your C. So leaky means some current flowing through the capacitor is leaked into the resistance. So maximum current starts flowing through RP and minimum current starts flowing through capacitor. So it is called as leaky because it leaks the energy to the parallel resistance. So it is called as a leaky capacitor. And we got the expression omega C RP. So okay, so remember when things are in series, it is Q is equal to X by R. When the components are in parallel, we have Q is equal to R by X. So we have verified that for finding the Q factor of L and C. We verified that with our usual formula Q is equal to X by R. It was working fine. We took the example of a leaky capacitor where R and C are in shunt, and we found that the formula is still holding good. So we got the formula is Q is equal to R by X, and after deriving using the usual Q factor formula, we got the answer to be exactly same as what it was intended to arrive at. So Q is equal to omega C